Alright, so in the last video I introduced what a linear combination is defined as. And in this video I want to connect the idea of linear combinations to something we've already seen in the prior two sections, and that is the existence and uniqueness in a linear equations, in a system of linear equations. And so what we'll do here is we'll look at a problem, and I'll go ahead and give you an example problem, and then we'll work through that to kind of build some intuition behind this. Now, one thing I want to point out is that this definition that we've used, the C, okay, and the V's and this, these are just general, they're arbitrary letters. We can use any letter that we want. And so what I'm going to do is I'm going to change it up a little bit here, and I'm going to bring us back to some of the stuff that we were talking about before, and that is I'll use, instead of V, I'm going to use A1. Okay. So I'm going to give you the vector A1, and that is going to be 1, -2, -5. And I'm going to give you the vector A2. Alright. And the vector A2 is going to be 2, 5, 6. Alright. And then I'm going to give you another vector, and I'm going to intentionally write this in a different color for a reason you'll see in the future sections. And we'll call this vector B. Now B is going to be defined as 7, 4, -3. Alright? And I'm going to pose this question to you. Can we generate B using the vectors A1 and A2? Alright? So, let's think about this question a little bit. And I'll add this on just to help clarify a little bit. Can we generate B using the vectors A1 and A2 in a linear combination? Alright. So, what are we asking here? So let's look at this word linear, these words linear combination, right? Well, we have the definition of what a linear combination is. That's right here, right? And we learned about linear combinations in the last video. Well, it looks like we have vectors, right? We have what is the equivalent of our V's, okay? And that is what the A is representing. And we have the equivalent of our Y, and that's what our B is representing. Remember, the distinction, the letters that we used in this general definition can be anything. And so in this case, we're just using A and B. And so what this question really amounts to is, can we find some scalars x1 and x2. Again, I'm going to change up the letters that we're using here just to kind of connect this to what we've already done before. Can we find some scalars x1 and x2 that satisfy a linear combination? A linear combination of B written in terms of A1 and A2. Alright, so in other words, we're looking for something that looks a little bit like this. Alright, plus x2, 2, 5, 6, equals 7, 4, negative 3. Now, right now this question might be a little confusing. You might not know where to go with this. So let's kind of massage what we have right here. All right, let's massage it a little bit and see if we can make this look like something we've already seen. So how would we simplify this equation? Well, what we could do is we could distribute the x's into the respective vectors. So let's go ahead and do that. So now what we have is actually we have 1 x1, right? So remember when we did scalar multiplication, things just get scaled right in. Scalars get just distributed across each element. So then we have negative 2x2, and then we have negative 5, excuse me, this should be x1, negative 5x1. Again, the scalar just gets distributed right into every element, okay? And then we have plus 2x2, and we have 5x2, and we have 6x2. Alright, and there is no scalar on that right hand side, so we still just have equals 7, 4, and negative 3. Alright, so let's continue to simplify this a little bit, and let's see what we can come up with. Alright, so we can add these two vectors together using our vector properties that we learned in a prior video. And what we'd have is x1 plus 2x2. And I'll go ahead and just put this in its own little vector right there, and then we'll have negative 2x1, right? Because we're just conducting element-wise addition here, plus 5x2. And then we have negative 5x1 plus 6x2. And again, this is just equal to 7, 4, and negative 3. Okay. So this is kind of starting to look a little bit like what you've done before, right? And so if it isn't already clear, one final step we can make is we could actually just convert this into a simple system of equations. So we have x1 plus 2x2 is equal to, what is that equal to? It's equal to 7. And then we have negative 2x1 plus 5x2 is equal to 4. Right? And then finally what we're going to get, we're going to get negative 5x1 plus 6x2 is equal to negative 3. And now this is starting to look like something that we've seen before, isn't it? Right? This is just a system of linear equations. Alright. Now, how do we represent a system of linear equations? Well, we can represent a system of linear equations using an augmented matrix. I'll go ahead and write this just so we're a little more clear on this, that has a coefficient of 1. And how would we write this system of linear equations into an augmented matrix? Well, what we would do is we're going to just grab the coefficients. So we're going to have 1, negative 2, negative 5, 6, 5, 2. I'll go ahead and write the line there. I think that helps a lot in terms of knowing that this is an augmented matrix that we're dealing with. And then that last column is going to be our B vector. It's going to be 7, 4, negative 3. Okay, so now this is an augmented matrix of our system of equations above. All right, and we know what we need to do in order to solve this system of equations. What we need to do is we need to use row reduction. All right, and I'll go through the process of actually row reducing this matrix in the next video. and simplifying it down to see what we can come up with. And once we do that, we'll make some conclusions about how we connect linear combinations and the idea of existence and uniqueness that we learned in the prior sections.